So, welcome back to our discussion on boundary layer theory, and specifically the last class was focused on looking at flow past a flat plate. So, we went through the derivation for Blasius boundary layer. So, after the entire exercise of the similarity variable, we obtained an equation for the boundary layer variable f, which allows us to compute the stream function. So, we had psi, the stream function, given as delta x u infinity or u external into f of eta. That was our boundary layer description. And using this similarity variable where eta is equal to y by delta x, we arrived at the relation that delta x is square root nu x by u infinity. So, this is 0 pressure gradient flat plate boundary layer. So, you have an angle of attack also that is 0. So, there is a uniform flow which is incident on a flat plate with a 0 angle of incidence, and we obtained this description starting from Prandtl's boundary layer equation, that finally the boundary layer equation using the approach given by Blasius turns out to be this nonlinear ordinary differential equation, which has boundary condition that f prime at infinity is equal to 1. This is the boundary condition, if you recall, actually comes from the fact that u at the edge of the boundary layer is, so u at the edge of the boundary layer is going to be u infinity. And the other two boundary conditions are f of 0 is equal to 0 and f prime of 0 is equal to 0. F of 0 is equal to 0 comes from the fact that the boundary layer is a no penetration boundary. So, this is a location of 0 stream function, and f prime of 0 comes from no slip boundary condition. So, using this we also computed, or rather derived, what were the expressions for velocity. So, we obtained that our velocity in the x direction is u infinity f prime of eta, and the velocity in the y direction is u infinity delta prime or rather let me write it as u infinity d delta dx eta f prime minus f, because prime I am reserving as differentiation with respect to the variable eta. Now, as I said, the way to solve this equation is, for any arbitrary value of eta, is to solve it numerically. So, you numerically solve the boundary value problem that you have here. Boundary conditions are given at the plate and boundary conditions are given at infinity, and this allows you to numerically solve this equation. There are various ways of doing it. One particular approach which is quite popular is known as called a shooting method. So, in shooting method, what you would do, you know the value of f at the plate. So, you know f0, this is known. You know f prime of 0, this is also known, but you do not know anything about the higher derivatives. It is a third order differential equation. So, you need 3 boundary condition. The boundary condition, the other boundary condition that is known is at infinity, f prime of infinity is equal to 1. This is what is known. Now, how do you do this? So, in a rough sense, the way you can start doing this is you make a guess for the second derivative. Assume some guess value. So, when you assume some guess value, this transforms into an initial value problem. Initial value problem in a sense that you know all the three conditions at eta equals to 0 and you can march forward in eta. You don't need to know anything else because you only need three conditions to solve this third order differential equation. So, you march in eta. As you march in eta, finally when you arrive at eta equals to infinity, do you get the value f prime of eta, f dash at eta equals to infinity at large value, does it approach 1? If it doesn't, then you calculate the error. So, f dash of infinity, whatever is computed numerically, minus 1 is what you need to reduce. So, you use this error in order to update your guess value. So, you made a guess and your guess obviously doesn't land you. You have to be extremely lucky to make the exact guess which corresponds to what is the value of f dash of 0. We don't know that f dash of 0 initially. So, the way to do this would be you make any arbitrary guess of f dash, f double dash, march forward in eta, arrive at large values of eta, see what is the error between your numerically computed f dash of infinity and how different is it from 1. So, this gives you an error that you have found. Based on the error, you go back and refine your initial guess. Do you increase the value a little bit? Do you decrease the value a little bit? So, there are formal ways of doing this. So, when you do it as a shooting method, you can often couple with things like a Newton-Raphson kind of a technique in order to how you keep updating the guess. There are other ways of doing it besides the shooting method where you can write this differential equation globally in terms of differentiation matrices and then use linear algebra procedures in order to invert those matrices and find the solution. So, there are various numerical approaches of solving this problem. Now, besides solving this numerically, you also have approximate solutions to this equation. I mean, think about this. This is something which was given by Blasius in 1908, long before you actually had access to scientific computation of any kind, forget of the kind that we have right now, where you can get an answer to this boundary value problem using any subroutine, whether in MATLAB or in Python, in a matter of few seconds, not more than that. It's that quick in terms of the computation. So, when Blasius did this, the only way of doing these things was primarily using very rudimentary computation, or in a sense rudimentary approximations. So, one approximations that was done was to find out what is the nature of the solution when eta is very small. So, you know that f0 is 0, you know that f dash of 0 is 0. So, what can you say about the function? The function cannot be a constant at eta equals to 0 because f0 of 0 is 0. The function cannot be linear for small values of eta at eta approaching 0. So, f of eta equal to a constant is not permissible because it violates f0 is equal to 0. For small eta, it cannot be a non-zero constant. Let me be more precise here. It cannot be a non-zero constant for small values of eta. It cannot be some constant times eta. This is also not permissible because this would give me a non-zero value of f dash of 0. So, finally, what you can argue that it should at least be a quadratic function, and it turns out it is indeed. When you do this as a series solution, you can work out what that series is. So, the series solution is f of eta is half C1 eta square, where C1 is approximately 0.332, and it's a series solution where the next term is actually not eta cube but rather eta to the power 5. So, it's quite tedious in terms of doing this calculation because you have the series, you need to work out a significant number of higher order terms in the series in order to find how the series behaves. The part which is more interesting to us is regarding what happens for large values. Because for large values, we know that f dash of eta goes to unity. Now, if f dash of eta goes to unity, that means f of eta would go to a linear function, because f dash of eta, for f dash of eta, for large eta to go to a constant, f of eta should be a linear function, and then you have subsequent corrections to that linear function. So, these again you can work out what is the asymptotic form of these constants. So, C2 is also approximately 1.72. So, I will come back to these values a little later when we are going to compute various things, because obviously during the lecture I can show you the numerical curve, but we won't be able to actually write a code and show it, but I will share on the side a small code which will solve Blasius equation. So, for now you will have to take my word of what the plot looks like. So, u by u infinity, which is f dash of eta for plotted as a function of eta, where eta is y u by nu x, because it is y by delta x is square root of nu x by u infinity. This function, you know that for small values of eta, f dash of eta is f of eta is quadratic, f dash of eta would be c1 eta, right. So, it is a function which will have a slope here that would be 0.332. That is the slope of this function. I have drawn it a little larger, it will not be this large, but it will be approximately 0.332. And then it is going to approach the line which is 1. This is what the velocity inside the boundary layer would be. Now, the part which you have to pay attention here, this is the streamwise velocity not plotted as a function of y. It is a streamwise velocity plotted as a function of the similarity variable eta, which means you can see this as u varying with y for fixed x or u varying with x for fixed y, because eta is this combination of y and x. So, what you can do, you can find the boundary layer profile at different stations in x, and you can see that those profiles will collapse onto each other, which means the streamwise velocity, let us fix a value of eta here. Let us just do this. Let us take a value of eta for the sake of our argument right now. Let us consider eta is equal to 3. Now, eta equals to 3 would be achieved if I fix my x as x star. I would get my y star to be 3 square root nu x star u infinity, right. But if you were to choose a value of x star which was, let us say, 8, so one sec, let me, so this already given the value of, so this is u infinity 3 nu, and now if I choose this x star to be 8, my y star is 3 8 nu by u infinity. Both have the same value of eta, which means the streamwise velocity is the same. That means as you go further and further downstream, you are going to encounter the same streamwise velocity at a higher height, right. So, initially This is just saying that if you now think of the plate, so here I am going to basically plot the velocity. So initially the velocity would look something like this. Then gradually the velocity would start to look like this. So if you draw the line, which is an eta equals to constant line, if you plot a line of constant eta, what would it look like? If you plot a line of constant eta, it is y is equal to some constant times root x. Correct? That constant basically being square root nu by u infinity into that particular value of eta. So lines of constant eta would look like this. So at each of these points, the velocity would be identical. So the velocity is varying in x. The velocity is not the same at different x location. If you make measurements of the velocity profile at different distances in the downstream direction, it's not the same. It's not what we have done earlier when we were doing all these fully developed problems, where we said in the flow direction, there is no variation of the velocity profile. Even when we did an unsteady flow problem, we said there was no variation of the velocity profile along the flow direction. Now, the velocity profile is changing, because think of what is actually going on. If this is x equals 0, exactly at the inlet, you have a plug flow or a uniform flow. It's only that once it enters the plate, the first few layers of the fluid have realized that, hang on, I cannot move as fast as u infinity. I have to be consistent with the fact that I am sliding over a stationary boundary. So the bottom layers of the fluid, the bottommost layers of the fluid have now gotten stuck to the fluid. So they have immediately come to a halt. But that information has not percolated all the way into the remaining part of the fluid. So gradually this gets percolated. So as it keeps moving, bigger and bigger chunks of the fluid is realizing that I am trying to move past a no-slip boundary. So in the unsteady flow, we had this diffusion of momentum which was propagating in the y direction, that was square root nu t. Here also you have a propagation of momentum due to diffusion that is happening as square root x. So you have a very similar process that is going on. As I keep moving further and further downstream, a larger and larger chunk of fluid is basically realizing the presence of a stationary or no-slip boundary. And that's what you are observing here. The velocity profile at different stations, by station I mean different locations on the plate, at different x coordinates on the plate, are different. They are not the same. So what this approach of similarity tells us, that if I were to actually look at the problem in boundary layer coordinate or in the similarity coordinate, then it's the same everywhere. If I track this line, which is the line of constant eta, on this line, the streamwise velocity is the same. So as you move to larger distances x, you will find the fluid moving with the same velocity, but at different heights away from the plate. That is the idea of this entire exercise, that it is capturing the streamwise diffusion that is happening. As you have your momentum diffusion, you are basically looking at the streamwise variation of your velocity field due to the longitudinal or due to the transverse diffusion of your momentum. So we have now more or less a lot of things that we need. So that was regarding the streamwise velocity. Now what about the vertical velocity? V. So V, as I wrote down, V is u infinity d delta dx eta f prime minus f. Now, d delta dx is d dx of square root nu x by u infinity, right? Now, square root nu by u infinity is independent of x. I can take that outside, and then when I do the derivative, I will have half x to the power half minus 1. So, I have half nu u infinity x. So, if I now plug it here, I have u infinity by 2 square root nu u infinity x eta f prime by f. So, this turns out to be 1 by 2 eta f prime minus f square root u infinity nu by x. Okay. So, instead of plotting v, we can plot the quantity which is v divided by u infinity nu by x as a function of eta, where eta is y by u infinity nu x. Now, this quantity is half eta f prime minus f. Now, what happens for small f? When I have eta being small, f was half c1 eta square. So, if I try computing this term, f prime would be c1 eta. So, now eta f prime minus f would be eta c1 eta minus half c1 eta square. Obviously, this is asymptotic, which means that I am ignoring all the other terms which are higher order that are there. Now, what is this? This will be half c1 eta square. For small values of eta, eta f prime minus f goes as half c1 eta square. What happens when eta is large? When eta is large, this goes as eta minus some constant c2. So, if I again substitute in eta f dash minus f, I will have eta f dash is 1 minus f, which is minus eta plus c2. So, this is c2. So, we have two information here, that limit of eta going to 0 of eta f prime minus f is equal to half c1 eta square, and limit of eta going to infinity of eta f dash minus f is c2. And we know these constants, the value of those constants are known. We have already written them down. So, c1 is approximately 0.332 and c2 is 1.72. So, what do you think the curve would look like for small eta for the velocity? This is the vertical velocity. What should it look like? A parabola. So, it should look something like this. It's not a linear curve. So, it will go up and then turn around. There will be a change of the curvature, and then eventually it will approach a constant value which is given as C2, which was 1.72. So, this is an interesting observation that the vertical velocity within the boundary layer doesn't vanish at the edge of the boundary layer. When we started this whole discussion, I said we have these three boundary conditions. The surface or the plate is no slip, no penetration, and the streamwise velocity should match the free stream velocity at the edge of the boundary layer. We didn't apply any boundary condition on the vertical velocity at the edge of the boundary layer. So, now what we have observed that the vertical velocity at the edge of the boundary layer is actually non-zero. So, from Blasius theory, when we do Blasius calculation, we arrive at this conclusion. So, there is a net mass flux that is there at the edge of the boundary layer. The vertical velocity is actually non-zero. So, if I now compute this, V is equal to half into 1.72. So, in the limit of eta going to infinity at the edge of the boundary layer, eta f dash minus f is 1.72 into square root u infinity nu by x. So, this is V. So, if I write this as V by u infinity, this would be 1 by u infinity square root u infinity nu by x. So, 1.2172, this is 0.86. So, this will be nu by u infinity x. So, at the edge of the boundary layer, the vertical velocity or the wall normal velocity is going to be 0.86 divided by square root of Rex. What is Rex? Rex is Reynolds number defined based on the location on the plate. So, it is a local Reynolds number. You have a particular coordinate x on the plate, x is a particular point on the plate. Based on that, you are actually defining what is your local Reynolds number. So, as you keep going progressively further and further downstream, Rex is actually going to keep on increasing. You will see larger and larger values. So, this is primarily telling you that as you go further downstream, the transverse velocity at the edge of the boundary layer is going to diminish. Now, this was regarding our velocity fields within the boundary layer. Now, we have also learned different ways of finding thickness of boundary layer. So, we know displacement thickness or delta 99. Sorry, we know the 99% thickness, then we know displacement thickness, we know momentum thickness. These are all based on integrals of the boundary layer profile, and we also know about energy thickness. All of these quantities can be computed from your expression from your boundary layer profile. So, the 99% thickness delta 99, so you have to find these things numerically from the boundary layer profile. So, the 99% thickness is approximately 4.9 square root nu x by u infinity, which is saying that delta 99 by x is equal to 4.9 divided by nu u infinity x or 4.9 by square root Rex. Okay. Similarly, now you can compute what would be your thickness of your based on the velocity profile. So, this was just taking the velocity profile, finding the location where it matches with the 99% value. Where would you find the boundary layer velocity matching with 99% of the free stream velocity? Then if you find using displacement, it will be 1.72 nu x by u infinity. Your momentum is around 0.664 square root nu x by u infinity. You can also similarly compute the energy thickness and it will all be in the same range. So, the point being made using this exercise is that your boundary layer thickness that you may measure, there are different measures of boundary layer thickness. How thick is the boundary layer? That thickness of the boundary layer is actually within the same range based on what criteria you are using. So, you can see from here when you look at each of these expressions that the thickness of the boundary layer is some constant square root x. So, the boundary layer is growing as you keep going further and further downstream, there is a growth of the boundary layer. The boundary layer is increasing and that growth of the boundary layer, obviously the exact numerical factor is arbitrary because the exact location of the boundary layer depends on how you interpret what is the boundary layer. 99% criteria is based on an actual value of velocity matching with the free stream. Displacement thickness is basically in terms of the displacement of the streamline. Momentum thickness is in terms of the deficit of momentum that is caused by the resistance offered by the surface. So, all of them are different interpretations of the same thing. What is happening due to a no-slip boundary is all that I have described here, that the velocity will not match with the free stream. Streamlines are going to get displaced in order to compensate for the mass flux. There is going to be a momentum deficit. Everything is tied with the fact that fluid is being slowed down as it moves adjacent to a surface. Now, which one you feel is more appropriate, you can take a call. But you can see all of them are within the same range of values. It's not like they're giving you wildly different answers. Again, this has to be computed here numerically. Later we will see there are different approximate ways of finding these various thicknesses. But coming to the final part of the Blasius discussion is what was the original motivation? The original motivation for doing this study was to actually find drag on a moving object or flow past a moving object. What is the resistance or the drag on the object? Now, here for us that object is a flat plate. We have flow past a flat plate. So, the first thing we will do is actually compute the skin friction. That is the shear stress that you have on the plate. So, we will try to compute what is the wall shear stress, and from that we will try to find the skin friction coefficient, which is the non-dimensional wall shear stress. So, these are things which are crucial in order to see the effect of boundary layer, because the starting point of boundary layer analysis is that there is a thin layer of fluid sticking to the surface where viscous effects are important and dominant. So, this entire exercise is targeted now to give us a measure or a value for what is the resistance that the surface offers to the fluid by making it adhere to it. So, let us first, so these are things which we will calculate, they are both connected, but first thing we will do is compute the wall shear stress. So, the wall shear stress is actually mu dou u dou y plus dou V dou x at y equals 0. This is tau xy or sigma xy. Now, do we need both the terms in the equation? If you remember in our channel flow, Couette flow problems, where we did fully developed problems, we didn't have this term because there was no vertical velocity in those problems. There was no transverse velocity in those problems. But here, we do have vertical velocities in the problem, right? So, shall we keep those terms? That is the question. Now, you can think from the approach of boundary layer. Approach of boundary layer tells us that if u is order u infinity and x is order L, then what is the scale for y? It would be delta. And what would be the scale for v? It would be delta by L u infinity, right? If it has to satisfy mass conservation, this is basically purely can be argued from mass conservation. Dou u dou x plus dou v dou y is equal to 0. So, if u scales as u infinity, x scales as L, then the boundary layer thickness is delta. That means v should scale as delta by L u infinity. There is no escaping this. Now, you check in the shear stress. The first term is u infinity by delta. The second term is, the numerator is delta by L u infinity and denominator is L. What can you say about the ratio of the two terms? This term is order delta square larger than the dou v dou x term, which means within the boundary layer approximation that we have done, dou v dou x can be ignored at leading order. So, at leading order, I can write my wall shear stress as mu dou u dou y at y equals 0. It's not because v is 0. This is not the argument that we used in channel flow or in plane Couette flow, where we said there was no vertical velocity, hence the shear stress at the wall was exactly mu du dy. Here it is mu du dy because du dy, which is the transverse gradient of the streamwise velocity, is order 1 by delta square larger. Delta is a small parameter. So, it is order 1 by delta square larger than the streamwise gradient of my vertical velocity. That is the reason why we are saying at leading order you can ignore that term. Okay. So, we have the wall shear stress now. So, that is mu du dy. So, mu du dy can be written as dou square psi dou y square at y equals 0. Now, you must remember what we had done, right? We had already calculated this dou square psi by dou y square. So, dou square psi by dou y square is u infinity f dash by delta. So, this is u infinity f double dash at y equals 0, which is equal to, y equals 0 corresponds to what value of eta? Eta equals to 0 divided by what is the denominator? Delta. Right? So, this is the expression for your wall shear stress. Now, here we have some help. We don't need to go and look at the plot, because if you remember that approximate analysis with which we started the lecture today, the asymptotic expressions for small eta and large eta. So, small eta, what is the expression? So, f of eta is half C1 eta square. So, what is f double dash of 0? C1 or 0.332. So, without actually relying on the numerical calculation, just for the purpose of wall shear stress. See, this is where there is some merit in sometimes thinking of these problems not just purely from a numerical perspective, but also using some approximate techniques. The approximate solution that we obtain, or the asymptotic solution that we obtain for small eta, is not sufficient for you to get the entire picture. But yes, it is indeed sufficient for you to get the wall shear stress. If your goal is to get the wall shear stress, and this is where you have to learn how to use combination of these tools. You cannot get entire information from a perturbation theory or asymptotic solution. But if you know the right way to use it, which is what we are doing here, that we didn't actually solve the problem, we took the plots, but we didn't do a numerical calculation during the lecture. So, if you do the numerical calculation, you will find what you have to calculate. But from the asymptotic calculation for small eta, which is the series solution, if you do, you will find that f double dash of 0 is 0.332. So, the wall shear stress is 0.332 mu u infinity by delta. Now, delta we already know what is delta, right? So, this is 0.332 mu u infinity, delta is square root nu x by u infinity. Now, if I want to write the denominator in terms of a local Reynolds number, what do I do? So, I have nu by, or rather nu x by u infinity. So, I can write this as, so I have x, so I want to remove x from the picture. So, I will, let me just, yeah. So, I will write u infinity x by nu into nu by u infinity into nu by u infinity. So, nu x by u infinity, I have written it as u infinity x by nu, and then because I have multiplied by u infinity by nu, I get a nu by u infinity, and I already had a nu infinity sitting in the problem. So, this is now 0.332 mu u infinity. The first term is Rex, and then there is nu by u infinity square, the square root of it. So, this becomes nu by u infinity. Now, what is mu by nu? What is dynamic viscosity by kinematic viscosity? It's rho, the density. So, this is 0.332 rho u infinity square by square root Rex. So, what you have here is that the wall shear stress is equal to 0.332 rho u infinity square by square root Rex. This brings us to what is known as the skin friction coefficient. Skin friction coefficient is defined as the wall shear stress scaled by, just like you scale your pressure with half rho u infinity square, you scale it again by half rho u infinity square, and this is 0.664 square root Rex. So, this is the value of your skin friction on the plate. So, if you were to plot the skin friction coefficient CF as a function of Rex on a log-log scale, not a linear scale, but on a log-log scale, what would it appear as? On a log-log scale, your y-axis is log and x-axis is log. What would be the nature of that curve for the skin friction coefficient? log CF is log 0.664 minus half log REX. So, it would be a line of slope minus half. This is what should come if you were to compare with anything. So, this is what the theoretical prediction is. So, Blasius' theory predicts that the skin friction coefficient is precisely this number. So, this is a very important thing for us to go forward with. Now, you can, now that you have your expression for shear stress, you can go ahead and try to compute the drag on the plate. So, the drag on the plate per unit width, because you are doing a two-dimensional problem. So, you have the plate, you say the plate is length L and you are doing the calculation where it is unit width. So, if I say drag per unit width on the plate is going to be 0 to L tau at the wall dx. So, this is 0.332 rho u infinity square 0 to L dx by square root Rex. Now, what is Rex? Sorry, this is rho infinity square 0 to L, Rex is u infinity x by nu. So, I can take all the constants outside, square root nu by u infinity 0 to L dx by square root x, which would be rho u infinity square root nu by u infinity and then into 2 root L. On integrating 1 by root x from 0 to L, you are basically going to get 2 root x between 0 and L, and that gives you 2 root L. So, finally, the drag per unit width is 0.664. Now, if I multiply and divide by L, then I can write this as 0.664 rho u infinity square root REL, where REL is u infinity L by nu. So, that is the drag that the plate experiences per unit width. Now, there is one assumption or one point we have made in the drag calculation, is that this is the drag on one side of the plate. If you think of your hand as a flat plate and you put it in front of a fan, there is wind that is blowing over your palm and also under your palm. So, the drag force that you would experience would be double of this value. So, this is drag per unit width on one side of the plate. If there is flow on both sides, you have to take twice this particular value. Now, few comments regarding this drag force calculation. What is the dependence on velocity? What is the dependence of the drag? If I just try to find how does drag change with change in velocity? There is a quadratic power here, but there is also a velocity on the denominator, a half power there in Reynolds. If you just say that I am increasing my velocity by a factor of, let us say, 9, how much would the drag increase? So, here drag goes as velocity to the power 3 halves. Okay. Why I am making this point is when you do this problem in the other limit, when the flow is very, very slow, it's a very low Reynolds number flow, there the drag actually goes linearly with velocity. Whereas from this flat plate calculation of boundary layer, the drag actually goes as 3 halves power of your velocity. So there are a lot of interesting things that you are getting from this calculation. Obviously, there are few things which we have kind of skipped over. We have not made a fuss about it, whereas it is actually a fuss. The first thing which is a fuss here is, if you look at the shear stress expression that you have here, is there a problem in that expression? What happens at the starting edge, at the leading edge, x equals 0? It's an infinite shear stress. The shear stress at x equals 0 at the leading edge is infinitely large. It turns out that in the drag calculation that didn't matter. Even though the shear stress was singular at x equals 0, it was a weak enough singularity that we could do the integration and give you an answer. So for the purpose of an integrated quantity like drag, it didn't matter and we got a final answer because it was a weak singularity. But it is a singularity nonetheless, which means whatever we have done here, and this goes back to the question of loss of memory of your initial condition. When we started Blasius calculation, I said we have lost memory of the initial condition. At the leading edge, at the tip of the plate, whatever we have done cannot be applied. So even though I have been doing this calculation as if presuming that I can access x equals 0, you cannot access x equals 0 in the framework of what we have done.